Hi students, here to walk you through chapter 5 on probability. So here we go. Okay, so you'll see that there is a lot of new vocabulary in chapter 5. Lots of definitions. Okay, so don't let that dissuade you. Chapter 5 is not a favorite, but you'll be okay. Just keep looking back at the video and contact me with questions, okay? So we start out by defining probability. What is a probability? And probability is some number that describes the likelihood that an event or a series of events will occur. It's always a number between 0 and 1. So a probability can't be a negative number, and a probability cannot be greater than 1, okay? So the result of such event or events is called an outcome. So that's the result of your event, which is called an experiment. Okay, so the experiment creates creates the probabilities. Okay, so it's an activity or a series of activities that results in an outcome, and that outcome helps us create our yeah, God. Okay. Wait. Hi students, I'm here to walk you through chapter 5, probability. There's going to be a lot of new definitions and vocabulary, so don't let that get in your way. All right, let's do it. Okay, so a probability by definition is some number that describes the likelihood that an event or series of events is going to occur. It's always a number between 0 and 1. So you know if a number is greater than 1 or negative, that it's definitely not a probability. Okay? The result of these events is called an outcome. Like for an example, say I flip a coin. The result of those flips is either going to be a head or a tail, and those would be outcomes. Okay, or if I roll a die, I'm either going to get a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and each one of those is called an outcome. Okay, an experiment is what we do to create that outcome. So the experiment would be the flipping the coin or the rolling the die or the choosing a card from a deck. I like to use those examples because they make sense to most people. You can wrap your head around them. Or selecting an object at random or something like that. Okay, and a simple event is the events broken down into their smallest components. In the book, they're denoted with an E sub I. So like E sub 1 would be the first simple event, E sub 2 would be the second simple event, E sub 3, etc. So like if you were rolling a die, E sub 1 might be getting a 1. E sub 2 might be getting a 2. E sub 3 getting a 3, and etc. Okay? Simple events, remember, cannot be broken down any further. So like say you rolled a die and you looked at the probability of getting an odd number when you roll that die. Okay? This isn't a simple event because there are 3 ways you can get an odd number, and they can be broken down smaller, right? That would be probability that you get a 1, or a probability that you get a 2, or the probability that you get a 3. Probability that you get a 1, or probability that you get a 3, pardon me, or the probability that you get a 5. Okay, So these would be simple events, the 1 or the 3 or the 5. Okay, so let's see. A sample space would be the collection of all possible simple events of an experiment. So let's say if we're going to roll a die, we might say the sample space is a collection of, and you might write that as a set, getting a 1, a 2, a 3, a 4, a 5, or a 6 when the experiment is performed. And if you were going to flip a coin, the sample space would look like head or tail, something like that. Okay? There are some rules of probabilities. Probabilities are always numbers between 0 and 1, as we discussed, for any event. Doesn't matter what the event is. If the probability is 0 of event E is impossible. And if the probability of event E is 1, event E is certain to occur. So the closer the probability is to 0, the less likely the event is to occur. The closer to 1, the more likely the event is to occur. And the sum, because in a sample space, you're considering every possible simple event of the experiment, when you add up all those probabilities, it always must equal 1. And you can think of it in terms of, I have considered everything that's going to happen, and when I perform this experiment, one of the things in that sample space is going to occur, right? I'm going to get a 1 or a 2 or 3 or 4 or 5 or 6. And so when I add up all the probabilities corresponding to that sample space, I should always get a 1. It's analogous to saying when I perform that experiment, something in that sample space is certain to occur. Okay? In our book, the author looks at unusual events. He defines this, an unusual event, as having a probability less than or equal to 5%. So when it's in that realm, he'll ask you in some of the homework questions, do you consider this to be an unusual event? And note that that's only his deal. Okay, so 2 ways to generate probabilities. One way, and they're both equally important. Okay. Okay. One way is the empirical approach to probability, which is strictly observational. So we perform an experiment a huge number of times, typically or ideally, and count the number of times that the event of interest occurs. So the probability would be that the number of times that the event occurs over the number of times the experiment is repeated. So let's say we were interested in what the probability of getting ahead is when a coin is flipped. And let's say we repeat the experiment 10 times, and we consider that to be large. Okay, so let's say in those 10 flips, we get 7 heads. So based on our empirical evidence, the probability of getting ahead when a coin is flipped is 0.7 or 0.70. Okay? So there's just a couple things wrong with that probability. Number one, every time we repeat the experiment, this number has a likelihood of changing, right? And another thing is that the number or the possible outcomes of the experiment are equally likely, and so that puts a different spin on how we should generate that probability, okay? But the empirical approach is a really good, what do I want to say? A very good way to calculate probabilities when the events are not equally likely. Let's say, for example, you're going on a vacation with your family, and you want to pick a safe airline. So you go online and you look at the safety records of all the different airlines. And you note that the safety record has to do with the number of miles that that airline has flown and the number of corresponding accidents in that number of miles. So it's an empirical probability, okay? Or something like, what's the probability that the ideal day to plant corn crops is March 1st? It depends on, they'll go back over the years and look at the empirical evidence of, what's the best day due to what has happened in previous years, et cetera, et cetera. Look at the almanacs, look at the weather patterns, look at the current weather pattern, and decide based on that empirical evidence, okay? So the empirical law definitely has its place, but it's not typical. Okay, the classical approach to probability is the other way that we can generate probabilities. And this is the probability for equally likely outcomes. So in our head flip experiment, if an experiment has n equally likely outcomes, in our head flip experiment that would be 2, right? Because you can get a head or a tail. And an event can occur in, actually this should be F. It was M in a previous book. In F different ways, then the probability of that event would be the number of ways that the event can occur. There's only one way I can get a head on a coin. Number of possible outcomes is 2. Number of possible, in fact, equally likely outcomes. And this should make more sense to us when we're looking at the probability that a coin toss comes up ahead. Okay. The law of large numbers in statistics says that if we were to repeat that empirical approach infinitely many times, so if we flip that coin again and again and again and again and again and again, infinitely many times, that the empirical probability would approach that classical 1/2 probability. Okay, so here's a problem from our book. In the game of roulette, you have a roulette wheel, which is shown in the picture. It's got 38 slots. And it's got a 0, a double 0, which are green, and then the slots 1, 2, etc. through 36, which are alternating red and black. So you spin a metal ball around in the wheel, it falls into one of the slots. So the sample space here, okay, the sample space is the set of all possible outcomes. So it would be 0, double 0, 1, 2, 3, and so on and so forth, all the way up to 38. 36. Okay? And again, those are all of the simple events. If we want the probability that the ball falls into the slot marked 8, so note in probability notation, you write the event in the parentheses, not the calculation, the event, however you want to describe it. So you want the event that you get an 8. There's only one way that an 8 can occur over the 36 equally likely outcomes, or sorry, 38 equally likely outcomes. And in probability, we generally write our probabilities in a fraction in lowest terms or a 3 significant digit decimal. So if you do the division 1 divided by 38, it's 0.0236, or sorry, 63. And 3 significant digits means after any zeros. So you go decimal, any zeros, then 3 digits. So to 3 significant digits, that probability is 0.0263. And what it means is about 2.63% of the time, the ball will fall on the 8 in roulette. Okay? And that's in infinitely many repetitions. So in part C, we want the probability that the ball lands in an odd slot, an odd number. So odd, let's see, we've got how many odds? We've got 36. 0 and 00 are not considered even or odd. So we've got 1 through 36 divided by 2, which would be 18 odd slots out of the 38 equally likely outcomes. And that would be 9/19 in lowest terms, or 0.474. Okay, so let me show you something on your calculator that's going to make your life so very easy. Okay, so especially if you don't like reducing fractions, here's what you do. Okay, so let's say we're going to put that 18 divided by 38 in our calculator. And you get this decimal plus more places, okay? So once you have this decimal in your calculator, you're going to hit Math, the Math key, and you'll see that the very first entry there is a little arrow that looks like that, and then the word frac. And it means take my answer and convert it to a fraction in lowest terms. So then you hit enter twice. Let me put this in parentheses because it's not what you hit. You hit enter twice, and then you get your fraction back in lowest terms. So you do the division, right? You get the decimal representation, then you hit Math, enter twice, and there's your fraction in lowest terms. It's really pretty darn sweet. Okay, in 5.2, we talk about the addition rule and complements. So let's say we're going to pick a card from a deck, and we want to calculate the probability that that card is a king or a queen. Okay, so how many kings and queens are there in a deck of cards? Let's see, there'd be 4 kings and 4 queens, so that's 8 cards altogether out of the 52 cards in the deck. Oh, hey, and let's try our little trick. So we're going to go 8 divided by 52. So that's 0.154 to 3 significant digits. And then we're going to hit Math, enter, enter. And we can see that that fraction in lowest terms is 2/13. Just love that. Totally makes the calculator worth its weight in gold. Okay. So now let's talk about these events, king and queen. So 2 events are called mutually exclusive if they both cannot occur when the experiment is performed. So if I'm going to pick a card from a deck, there's no way on that one card I can get both a king and a queen. It's going to be one or the other or something else, but I'm not ever going to be able to, I'm not ever going to get a king and a queen. So the events king and queen here are considered to be mutually exclusive, okay? Mutually exclusive can also be called in some cases disjoint. So some use one terminology, some use the other. I like mutually exclusive personally. So the addition rule for mutually exclusive events says that if we've got 2 events A and B and they're mutually exclusive, we can add their probabilities if we're looking for the probability of A or B. So you may remember the operators from algebra, the ands and the ors. Remember, the and is the intersection, the or is the union. Sorry, I lost my train of thought. Yeah, so the operators and and or are also very important in statistics, okay? So you're going to want to really pay attention to those little statements in there, okay? So the probability of a king or a queen, let's do this. Probability of king, oh, hang on. The probability of a king or a queen is going to be the probability of a king plus the probability of a queen. Okay? And the events are mutually exclusive, so we simply add the probabilities. 4 50 seconds plus 4 50 seconds. And we get the same probability that we got in the first place. Okay? Note that the addition rule too can be extended for 3 or more mutually exclusive events. So let's say you wanted the probability of a king or a queen or an ace or a 10. You would just calculate all those probabilities separately because they're all mutually exclusive and add them all up. Okay, so here is an example. It's number 30 in 5.1. And it is a probability, supposed probability model showing the distribution of the number of rooms in a U.S. housing unit. Okay. So to verify that this is a probability model, remember that the conditions are that all of the probabilities have to be between 0 and 1. And we can see that they are. That's a good thing. Okay. And B, that the sum of the probabilities over the sample space equal 1. And if you add these guys all up, you'll see that they do equal 1. Exactly. So that is indeed a probability model. And in chapter 6, actually, we start calling these probability distributions. Okay? In part B, we want the probability that a randomly selected housing unit has 4 or more rooms. So we would say the probability that the rooms are 4 or more, greater than or equal to 4, would be, okay. So note that there's no overlap here. Either a housing unit has 1 room, or 2 rooms, or 3 rooms, or 4 rooms. You can't have both 2 and 3 rooms, or 6 and 4 rooms. So all of these events are mutually exclusive. So the probability that your number of rooms are greater than or equal to 4 is equal to the probability that the number of rooms is 4, or the probability that the number of rooms is 5, or you have 6 rooms, or you have 7 rooms, or you have 8 or more rooms. And then you simply write down all the probabilities. Okay, probability of 4 rooms would be the 0.183. The probability of 5 rooms is the 0.230. 6 rooms is the 0.204. 7 rooms is the 0.123. And then 8 or more rooms is the 0.156. And you just simply add all those probabilities together and you should get 0.896. And that means that if a U.S. housing unit is chosen at random, the probability that it contains at least 4 rooms is 0.896, or you would choose a housing unit with 4 or more rooms 89.6% of the time. Okay? And if the probability isn't less than 8, right? The complement of that would be 8 or more. And in this case, it's an easier calculation because it's only one number. So you can go 1 minus the probability that the number of rooms is at or more than 8. We'll also see this concept a lot in the next section, or next chapter, chapter 6, specifically 6.2. So the easiest way to get there is 1 minus 0.156, which equals 0.844. So 84.4% of the time, you would select a housing unit in the U.S. with less than 8 rooms. Less than 8 rooms. Okay? All right, where are we? We're on D, right? Before we go on to D, let me clean this thing up. I love this part. You just highlight the whole thing. Grab it. A chunk. Oops. There we go. Okay, so part D. Okay, what's the probability that a randomly selected housing unit has from 4 to 6 rooms inclusive? That means including the endpoints 4 and 6. Okay, so it would be the probability that the number of rooms is between 4 and 6. And the equal signs imply that those endpoints are included. Okay, so it would be the probability that it has 4 rooms, or 5 rooms, or 6 rooms. And you would take the 4.183, add the probability of 5 rooms, 0.230, and add the probability of 6 rooms, which is 0.204. And altogether, that would be 0.617. And so, and you'll find that most of the time decimals are going to make more sense than fractions, because sometimes the fractions are really gigantic, you know, big time denominators and stuff, and they don't really make a lot of practical sense. So the probability of 4 or 5 or 6 rooms in a randomly selected U.S. housing unit would be 0.617, or would occur 61.7% of the time. Okay, one more. What's the probability that a randomly selected housing unit has at least 2 rooms? Okay, so let's try using the complement again. So the probability that the number of rooms is at least 2 would be 2 or 3 or 4 or 5 or 6 or 7 or 8 or more. And wouldn't it be nicer to just say, how about 1 minus the probability that X is at least 2 rooms complement, or 1 minus the probability, so the complement of at least 2 rooms would be the probability of 1 room. Oops. So it would be 1 minus 0.005, which would be 0.995. And this is equivalent to saying 99.5% of U.S. housing units are at least 2 rooms. Okay, let's go on. Okay, so now let's talk about a new experiment. Let's say we want to pick a card from a deck. What's the probability that we get a king or a heart? Okay, so we just talked about the fact that, I'm going to switch colors again. Blue. So we just talked about the fact that the or statement means that we can add the probabilities. So we would say probability of a king, we can just put a K for king, plus probability of a heart. Okay, we know we can add those together. So the probability of a king, okay, we've got 4 kings out of the 52 equally likely outcomes. And we have 13 hearts out of the 52 equally likely outcomes. But then go back. So your step 1 is the or statement and adding the probabilities. But your step 2 is looking at the events and thinking, can they both occur when the experiment is performed? In other words, if we pick a card from a deck, can we get both a king and a heart? And the answer is yes, isn't it, when we get the king of hearts? So when this occurs, when the events are not mutually exclusive, we have to subtract back out the overlap, which is the probability of getting a king and a heart, or the king of hearts. If you think about it, in this piece, we counted all 4 kings, including the king of hearts. Okay? And in this piece, we counted all 13 hearts, also including the king of hearts. So we have to subtract the king of hearts back out again because we counted him twice. So this part is like the overlap of whatever stuff you counted twice. So you would get 17 minus 1, 16 50-seconds, or in a 3-place decimal, that's 0.296. Or in a lowest case fraction, it's 8/27. So if you have a half or something like that, you know, a third, a fifth, 2/5 even, the fraction might make sense. But once you know, there are not that many fractions that you know, they make that much practical sense to us. So a lot of times the 3 significant digit decimal is much better. Okay, so this brings us to the general addition rule, which says if A and B are any 2 events, then the probability that A or B occurs is the sum of the probabilities minus the overlap. And that is the probability that A and B both occur when the experiment is performed. And note that if A and B do happen to be mutually exclusive, then this part drops out because the probability that A and B can both occur is impossible. That part is 0. So let's try a problem. This is called a contingency table. And it is a cross-classification of 2 variables. Okay, cross-classification of 2 variables. So you've got people who are employed or not, so their employment status, and whether or not the person is male or female. Okay, so that's the classification, the two variable classification. Okay, and these calculations are in millions. So the first thing you want to do when you're dealing with a contingency table is do a row total and a column total. So we add up the males, we get 11.3 million. Notice that this data is from the U.S. Bureau of Labor Statistics. We add up the females, we get 10.5 million. We add up those employed. Okay, we're going to have total column too. A total column. We're going to get 19.4. And if we add up those unemployed, we're going to get 2.4. And when you add up your column totals and your row totals, they should both equal 21.8, which should be the number of people in the civilian labor force ages 16 to 24. Okay? So let's go to part A. What is the probability that a randomly selected 16 to 24-year-old individual is employed? Okay, well, how many people are employed? So you look at your employment category. There are 19.4 million employed. I'm going to write probability employed, abbreviated. So we have 19.4 employed out of the 21.8 million total. Notice the number employed doesn't designate whether they're male or female, and that number is 0.890. These are kind of nasty fractions even when you simplify them, so let's stick to decimals. Okay, and then part B is what's the probability, so that's A. There we go. Part B is what's the probability that a randomly selected 16 to 24-year-old individual from the civilian labor force is male. So the probability that that person is male. And now you're going to go to your data table and you look at the total number of males, whether they're employed or not, over the 21.8 million total in our group here, and we should get 0.518 as our decimal. Okay. So 51.8% of the civilian labor force is male. 89% is employed. Okay. This had to be a while ago, huh? Part C is what's the probability that they're employed and male? Employed and male. And in a contingency table, we can go to the cell, okay, here's employed males. Right? Employed, male. So we're just looking at that one cell that cross-classifies both employed and male members of the civilian workforce. Out of the 21.8, when we reduce that, we get 0.454. So 45.4% of the civilian workforce is both employed and male. Okay, now part D. And hopefully that the non-mutually exclusive calculations will make sense to you here. Okay, so what is the probability that a randomly selected 16 to 24-year-old individual from the civilian labor force is employed or male? Okay, so the probability that the person, so the and the or, different operators, that they're employed or male is, okay, because of the or, we're going to do the probability that they're employed plus the probability that the person is male. And then we stop and ask ourselves, are these two events mutually exclusive? Can we select someone out that is both employed and male? And the answer is yes. We did it right here, right? Part C. So we're going to have to subtract out that overlap. So it's minus the probability that the person is employed and male. Hope you can read my writing. This pen is nice, but it's still, well. Unfortunately, I have the handwriting I have, so it's not very nice. Okay, so the probability that they're employed, that would be everybody that is employed, whether they are male or female. So that would be the 19.4 over the 21.8 plus the probability that they're male. So that would be the total males, whether or not they are employed, over the 21.8 total. And now notice notice that when we calculated the probability that the person was employed, we did this whole group. And when we calculated the probability that they were male, we did this whole group. So the probability that they were, I'm just kind of playing around trying to use this highlighter kind of thingy, but the probability that they are male and employed got counted twice. Right? They got counted in this cell right here. So we're going to have to subtract that back out again, the 9.9 out of 21.8. When you do the addition, subtraction, and division, you end up with 0.954. So the probability that you would choose somebody that was employed or male would happen 95.4% of the time. Okie dokie. Let's go on. Okay, so here we are talking about the complement again. So we talked a little bit about that already. Let's say if I'm going to pick a puppy from a litter. I'm not going to flip the little critter over to see if it's male or female. There are 4 males in the litter and 1 female. Just cute little squirmy puppies. What's the probability that I pick a male complement? So it would be 1 minus the probability that I do pick a male. So this is that I don't pick a male, right? It's 1 minus the probability that I do pick a male, which is also you can write it as the probability that I pick a female in this case, because there's only one or the other. So male complement would be female, female complement would be male. Okay. Okay. So the probability that I pick a male complement would be 1, because there's only one way that I cannot choose a male, over 5 cute little puppies. All right. So the complement and the probability, again, they always have to add up to 1. Okay? Because, again, you are considering everything in the sample space, either with the event or its complement. Okay? And you add them together, you're going to get everything in the sample space. And because they're just 3 numbers, it's like if you have x plus y equals z, okay? You can solve that equation for x, you can solve it for y, and here, of course, it's solved for z. So there are other ways of looking at that, and it's nice because sometimes finding the complement of the event is actually easier than finding the probability of the event. Oops. Okay, here's another problem. Okay. According to the U.S. Census Bureau, the probability that a randomly selected worker primarily drives a car to work is 0.867. So again, we're still in 5.2, I believe. And this would be number 39 in the book. Okay. Probability that a randomly selected worker primarily drives a car to work is let's just try black for a while, 0.867. And the probability that they primarily take public transportation is 0.048. So the probability that they drive is equal to 0.867. And the probability that they take public transportation is 0.048. Okay, so what, part A, what is the probability that a randomly selected worker primarily drives a car or takes public transportation to work? Okay, so the probability that they drive or take public transportation. Okay, so the or tells us that we can add the probabilities. Okay, and then we ask ourselves, are the events mutually exclusive? Can they both primarily drive and take public transportation? And I don't think so here. If it's primary, they're either going to drive or public transportation or something else. Maybe they could ride a bike or something, who knows. So we would just add the probabilities, 0.867 plus 0.048, my plus there, and add them together, we get 0.915. So 91.5% of people primarily take public transportation or drive to work. Okay, part B. What's the probability that a randomly selected worker neither drives a car nor takes public transportation to work? Wouldn't that be 1 minus the probability that they do drive their car or take public transportation? Which would be 1 minus what we got in the last calculation, right? 0.915. And that is 0.085. So just 8.5% of people do something other than drive or take public transportation to work. Maybe they walk, maybe they ride their bike, whatever. So in part C, what's the probability that a randomly selected worker does not drive a car to work? So it would be the probability of drive complement, which would be 1 minus the probability that they do drive. Wait a minute. Right. Okay. Which would be 1 minus the probability that they do drive is 0.867. And that ends up being, let's see, 0.133. Put boxes around these. They're getting kind of lost in there. So let's see. Can the probability that a randomly selected worker walk to work equal 0.15? Think about that a second. If they primarily walk to work and added with those who primarily drive and take public transportation, wouldn't that be more than 1? So right away I'm going to say no, because the sum of the probabilities is already bigger than 1, and there's got to be other ways to get to work. And that can't happen. Okay. Let's talk the multiplication rule. This is 5.3. And hang on a second. I'm going to get some water. Okay, thank you. Okay, here we go. We're going to roll 2 die. And the die are distinct. The die are distinct, okay? They have to be, you have to consider one die being a distinct object, the other one, even if they look just the same, being a distinct object. What's the probability that I get a 6 on die 1 and a 6 on die 2? Notice this is an AND statement. Maybe I'll go back to red for a while. This is an AND statement. So the probability that they get a 6 on die 1 and a 6 on die 2 is going to be a multiplied probability. If you look at each die individually and you multiply their outcomes 6 times 6, you get 36 equally likely events that can happen. So this should make sense because the probability of getting 6 on one die is 1 out of 6. And the probability of getting 6 on the other die is also 1 out of 6. So there is only 1 out of 36 equally likely outcomes that you're going to roll 2 die and get both 6s. And that decimal is 0.0278. So that will happen less than 3% of the time. You'll roll 2 die and get 2 6s. Okay. With the AND situation, let's talk about independence. So 2 events are independent if their outcomes don't affect each other. In other words, I roll this die. Maybe I roll this die at the same time. Maybe I roll it separately. It really doesn't matter. But whatever I get on this die, is it going to influence whatever happens to the outcome of this die? No. So we consider those outcomes to be independent, meaning they have no effect on one another. Okay? And you have to consider independence for the multiplication rule or the AND statements. Okay? So the multiplication rule for independent events, it says if A and B are independent, then the probability of A and B both occurring means you multiply the individual probabilities. And this can be extended for 3 or more. So let's say you were rolling 5 die, like you're playing Yahtzee. What's the probability that you get a 6 on one and a 6 on the second and a 6 on the third? And those would all just be multiplied probabilities. Okay? The summary, there's a nice summary of probability rules in your book on page 253 if you're interested. Okay, and here's a problem out of your book. About 13% of the population is left-handed. So, given this, okay, it means that the probability that you randomly select a person from the general public and they're left-handed would be 0.13 if 13% of them are left-handed, okay? And there are a lot of people in manufacturing who'll be interested in this fact, right? You got left scissors, left golf clubs, left baseball gloves, you know, all kinds of stuff for left-handed people. Left-handed batters in baseball, they need their little ear cover protector thingy on the opposite side of their head, and so on and so forth. Okay. So if 2 people are randomly selected, what's the probability that both are left-handed? Okay. So 2 people selected. Probability that the first is left-handed and the second person is also left-handed. So we've got that and statement in there. So it means that we would multiply the probabilities. The probability that the first is left-handed times the probability that the second is left-handed okay, and probability that any one person is left-handed is 0.13. So we have 0.13 times 0.13, or 0.13 squared. And that would be, let's see, 0.0169. So it means that less than 2% of the time, if you randomly selected 2 people out of the general public They would both be lefties. And now think about it. Is the fact that the first person is a lefty, is that going to affect whether or not the second person is a lefty? And if you're choosing people within a family, that might have an effect. But just choosing two people from the general public, it should not have an effect. Okay, now let's get to the next question. What's the probability that at least one is right-handed? So the probability B-L-E-A-S-T, at least one is right-handed. So that would mean, okay, you've got two people. That means that either the first is right-handed, or the second is right-handed, or they're both right-handed. Easiest thing to do here is to use the complement. So if at least one is not right-handed, it would mean that they are both left-handed. Okay, so if we can have either 0 or 1 or 2 of them right-handed, at least one would encompass 1 or 2. The complement of that would be that neither of them, or 0, are right-handed, or they're both lefties. Yay. And we got that up here. So it would be 1 minus 0.0169, or 0.9831. When you see that those words at least, whoops, and I guess you could yeah, I just found a new eraser on my pen. That's pretty groovy. You could just round that to 3 significant digits if you want. So 0.983 is the probability that at least one of them is right-handed, which makes sense because the probability of them being, it should make sense, because the probability of them being both lefties is so small. Okay? So, let's go on. Okay, 5.4. In 5.4, we talk about the general multiplication rule, which is when the events are not mutually exclusive, okay? I'm sorry, independent, when the outcomes are not independent. Okay, so a conditional probability is the probability of an event occurring given that another event has occurred. So it's denoted like this: the probability of A occurring given that B has already occurred. Okay, so that vertical line means given or such that. So the general multiplication rule says the probability of a sequence of any two events occurring is, if you're looking for the probability of E and F, you multiply the probabilities. And the second probability you're going to consider is the probability of F given that E has occurred, which was back here. And if E and F are independent, then you're just back to, where we've already come. Okay? So let's say, for example, let's see, what do I have coming up? Do I want to do an example here? No, we'll wait. Okay. So to find the conditional probability, so again, these are just 3 numbers. Probability of E and F is a number, probability of E is a number, probability of F is a number. So it would be like X equals Y times Z. And you could find, if you have any 2 of those numbers, you can find the third, right? So a lot of times you can find the conditional probability if you have the other 2 pieces. You just look at it as a ratio instead. You would just solve for that value. Okay. Here's another example. Due to a manufacturing error, 3 cans of regular soda were accidentally filled with diet soda and put into a 12-pack. Suppose that 2 cans are randomly selected from the 12-pack. Okay, so we have a 12-pack, right? So we have 12 cans of soda. 3 are accidentally filled with the diet, heaven forbid. And then 9, that means would be regular. I'm going to just put reg. Okay, so what's the probability that okay, so 2 cans are randomly selected from the 12-pack, one after the other. It implies one after the other, okay? So what's the probability that they're both diet soda? So you're looking at the probability that the first is diet, and also the second is diet. It wouldn't be the first or the second is diet, right? Because it's saying they both contain diet soda. So if you have to like think about it in terms of the and the or, and then go back and switch, that's fine. Okay, so this is then the probability that the first is diet. And once you've opened that can and discovered that that's a diet soda, then the second probability is that the probability that the second is diet. Okay, let's say here the first is diet. The second is diet, given that the first was diet. And that calculation would be, okay, so diet. Okay, so I've got 3 diet out of 12 cans. 3 ways you can get a diet soda out of those 12 cans. And then now you've opened one of the cans, so you only have 11 cans left. And you've opened one of the diet sodas, so you only have 2 out of the 11 cans left with diet soda in them. Okay, so that would be multiplied across 6 over 132. And in a 3 significant digit decimal, it's 0.0455. And so 4.5% of the time, just about, you would get both diet sodas if you open 2 cans from that 12-pack. Okay, part B. What's the probability that they were both regular soda? So again, probability that they're both regular, it'd be the first is regular, and the second is also regular soda. So you multiply the probabilities. The probability that the first is regular, you've got 9 cans of regular out of the 12 total cans. And now you've opened a can, so you only have 11 left. And furthermore, you've opened a can of regular, so you only have 8 cans of regular left. So that would be 0.545 when you multiply across and reduce your, and do the division rather. So 0.545. Okay. And that should make sense because there are a lot more cans of regular than there are of diet, right? And then part C is, what's the probability that one is diet and one is regular? Okay. So the way you can get a diet and a regular, you could get a regular then a diet, or a diet then a regular, and you have to consider them both. So get this. So you're going to go probability that you get a diet, and then the probability and you get a regular, given that you've just got a diet, or the probability that you choose a regular, and, isn't this insane, the probability that you get a diet given that you just got a regular. Crazy, huh? So the probability that you get a diet, okay, so you have 3 diet in 12 cans. And, okay, so you've opened 1 diet. So that only gives you 11 cans, but you still have your whole 9 regular cans. Okay, so regular, given that you got a diet, 9 regulars left, all 9 regulars left, and only 11 total cans. Okay. Got this little spot thingy that helps me erase. Okay. Or the probability that you choose a regular, so you have 9 regulars out of the 12 cans, and, okay, you have 11 cans left, and all 3 of the diets are left. So multiply, add, then divide. You should get 0.409. So close to 41% of the time, you're going to get 1 diet, 1 regular. Okay, and to wrap up this chapter, we're going to talk about counting techniques. This might be kind of funny to you because, you know, who doesn't know how to count? But counting is really a vast area of statistics. It has to do with a whole bunch of interesting things like queuing theory, which is how people wait in line. Note that now when you go to Disneyland or Magic Mountain or something like that, they give you like a little buzzer thingy to come back. You make a reservation to come back and get in line for your ride. And the reason being is that they like you out walking around and spending money, right? You're not going to be spending any money if you're standing in line for a ride for 2 hours. Okay, so they're pretty smart. Stuff like that. How many tellers should you have open on 4 o'clock at your bank on Friday afternoon? If you're, say, a FedEx driver and you've got a bunch of stops to make, what is the best route for you to make, the best, most efficient, shortest route for you to make all your stops? Stuff like that. And also, if you can think about, like, say you worked in a big, giant office building. Say if you just worked at the college, how much wire there must be at the college that connects all of our computers and phones and faxes. And so counting also has to do with routing problems of physical stuff like wires and stuff like that. So this probability is virtually an endless topic of study. You could study it forever. So, okay, so combinations is the number of combinations of, if you start with n distinct objects and you pull them out r at a time, how many different combinations are available? Like today in class, we did this in my face-to-face class, and there were 38 of us there. And I said, okay, let's say there are 38 of us here. And let's say we did an awesome class project, and the American Statistical Association is going to pay 3 of us to go to Hawaii and present our project. And everybody wants to go because we all want to go to Hawaii. So how many groups of 3 different people could be selected from 38 individuals? Okay, so the n is your number of objects to start with. Your r is the number in the group that you want selected out. Okay, so to calculate that, you would go 38 factorial Recall that 38 factorial, come down here a second. 38 factorial would be 38 times 37 times 36 times 35 times 34, all the way down to 1. Okay? 0 factorial is defined as 1, and 1 factorial is also defined as 1. Okay, so we have 38 factorial over r factorial, which would be 3 factorial, and then times n minus r factorial. So that would be 38 minus 3 factorial. Okay. So 38 factorial is going to be 38 times 37, 37 times 36 times 34. My pen is getting testy here. That's a 4. Times 33 all the way down to 1. Oh, I got some more room over here. Let me fix this. Okay, 36 times, oh, I forgot my 35. Ooh, good God. Here, let me fix this a bit. Okay, 38 times 37 times 36 times 35 times 34 times 33 all the way down to 1. There we go. 3 factorial is going to be 3 times 2 times 1. And, oops, that's a times. And then 38 minus 3 is going to be 35 factorial. So this part is 35. So that's 35 times 34 times 33 all the way down to 1. Okay, so now we can cancel like crazy. So we're not going to end up having to do these by hand because our calculator will do this, but they really aren't not that bad. So 35 all the way down to 1, all those factors are going to cancel with all these up here because they're all just multiplied. Isn't that wonderful? And the 3 times 2 down here is 6, and that'll cross-cancel with a 6 in the 36 and leave us a factor of 6. So it's going to come down to 38 times 37 times 6, which is, whoops, got my calculator right here, times 6. I get 8,208. So in our classroom of 38 people, there are over 8,000 different ways that we can select out a unique group of 3 people. Pretty amazing, huh? The numbers get really big really fast. So the n objects have to be distinct. There cannot be any identical objects. Once an object is selected out, you can't reselect it. And the order doesn't matter. Like in our case here, the 3 people, they're going to go to Hawaii no matter what. If they're in the group, they're going to Hawaii. Now, let's say if we had 38 people and we were going to elect a president, a vice president, and a secretary, how many different slates of candidates could we get? Then the order would matter, because if the same 3 people were in on the board, they could have different positions. So that would be called permutations, where the order within the group does matter. Okay? But we're only going to do combinations. So I think I left a blank page. Did I? Right on. Okay, so in your calculator, okay, let's say you have n equals 38 and you have r equals 3. Okay, here's what you do. The command in the calculator comes up n choose r, like that. So what you want to do is type in your n first, then go get the command, then type in your 3 and hit enter. Okay? So the 38 has to be on like the side with the n, and the r has to be like on the side of the command with the r. Okay, so here's what you're going to do. You're going to type in your n, then you're going to hit your math key, And then you're going to hit 3 right-hand arrows. And then you can see the NCR is number 3. So that'll drag the NCR to your home screen. And then you'll hit the R value. So this is your N value. This is your R value. And then you'll hit enter. But these steps always are the same. So try that with me real quick. Let's say we have 40 objects. And we want to choose them out 6 at a time. So you're going to type in 40. That's your N. Then you're going to hit math, right, 3 to get your NCR. And then you're going to type in your 6, which is your R. And the number of ways you can select 6 items out of 48 items, let's see, is 3, 8, 3, 8, 3, 8, 0. So 3,838,380 different ways. Okay, so that's all we're doing in 5.5 because this is part of something that comes up in chapter 6. So I just wanted to briefly go over that. So, wow. My throat is dry and I'm ready for a glass of water. Thanks. I hope that this is helpful for you. And have any questions or comments, please feel free to shoot me an email. Take care.